Thank you very much for the opportunity to visit. Boston's a lovely city to visit, and I hope at some point when travel is permissible that will be in the cards. But nonetheless, the scientific exchanges and discussions I've had today have really been very enjoyable and I believe productive, and hopefully that'll continue with the seminar. So welcome everyone. I've changed the title as speakers are known to do with their seminars because the topic was just expanding. So I focused a little bit more on polymer conformations and dynamics in kind of two categories under rigid confinement and in polymer nanocomposites. So I want to start by thanking people and funding sources. We've been working in nanocomposites for a long time. I'm really just focusing here on the list of folks who've worked really on the dynamics side with the polymer or the particles moving. And so in particular, I also want to thank Russ Composto and Rob Riegelman. Rob's in our chemical engineering department, and my group collaborates with him a lot on nanocomposites. And capitalizing on his expertise in molecular dynamic simulations, and then Russ Composto with regard to polymer dynamics and polymer diffusion. And so, you know, this is Zoom. Many of you are probably at home wearing slippers. So, you know, it's going to be a little more relaxed perhaps, you know, because of the Zoom format. And I'm going to avoid some of the truly nitty-gritty details, because I think that's a little harder to do over Zoom. So I'm hoping I give you a flavor of what we do and the results we have, but the nitty-gritty experimental details, I've put my website on here so that you can go read the details in the papers. Okay, and one more word of thanks. So again, the primary papers I'm going to build upon for today's talk are by these four postdocs and graduate students across the top, and then the two collaborators, Rob and Russ, shown there on the bottom. Okay, so polymer nanocomposites. It's actually a very large collection of materials when you think about all the different parameters that you can choose when you design a polymer nanocomposite. Obviously, you choose the polymer. You choose which chemistry the polymer is. You choose its molecular weight. You choose its architecture. These are all the polymer variables. And then independently, you get to choose the nanoparticle properties. And so the composition of the nanoparticle, whether it is surface functionalized with just a small functional group or a polymer brush, as well as the shape and size, and then the shape and size dispersity of the nanoparticles. And so after you have these two components selected, and that's assuming you're only using two components, you can certainly do mixtures of polymers and mixtures of particles. We're not going to do any of that today. But once you have a polymer and a nanoparticle selected, you can put them together at different blending ratios. Again, you can control how the interaction is between the polymer and the particle. And then there's a whole plethora of processing conditions. And like many other polymer-based or soft matter-based materials, the processing really matters. You can get caught in local thermodynamic local minimum rather than going to the global minimum in free energy. And if the particles are anisotropic, then you also have topics of orientation. So it's a big field. And what I also want to highlight is that it is not a new field. As much as we want to think nano is new, I just want to show enough respect for the polymer nanocomposite work that has been going on for many decades. And the classic example of that is car tires. You know, natural rubber by itself is okay. You put in some carbon black, it's much better wear resistance. So that's kind of the historic piece, but the futuristic piece, I think, is still quite wide open. And I was really enjoyed hearing about some of the nanocomposite work going on at MIT, because I think it's actually looking in that direction with a variety of different particles that have different sorts of properties. If we look here, and then you can put different functionality on it and different polymers for the matrix, and then you have a whole range of different properties. And so this was just an attempt in this review article that Sanat and Brian and Rich and I wrote a couple years ago. This is just really an attempt in a visual to kind of express how diverse the material is and how much opportunity I think there is in polymer nanocomposites. Okay, so what I'm going to focus on today, though, is really the dynamics. And so how the polymer moves and how the nanoparticles move inside nanocomposites. And the dynamics of the polymers and the nanoparticles certainly are important for properties. So just a few examples from literature. So this is the one from Zach's dissertation group. So from Benny Freeman's group, there's this result showing that unexpectedly, you can both improve permeability and improve gas selectivity when you increase the nanoparticle concentration, right? So for gas permeability, you know, the very local polymer dynamics at the nanoparticle surface is what dictates this gas transport property, right? So there's an example of polymer dynamics in the nanocomposite are impacting a property. Another example from imprint lithography is the flow properties. So here's an example where if you just have a neat polymer and you make fine lines, if there's a little bit of heat, it disappears altogether, but it's much more resistant to flow if the nanoparticles are there. And so these are just line traces across these different structures before and after annealing, right? So the nanoparticles add dimensional stability. And again, this is how the polymers and the particles flow. It's dynamics of that, which impacts this property. And finally, in the case of self-healing, it might be a little hard to see, but down below here, this yellow domain is actually a nanocomposite, and it's coated with silica. And there's, you know, a variety of different, you know, devices where you're going to have this sort of structure, but the silica can be delicate. And so the composite below, if there's enough mobility of the nanoparticles can bloom and coat the cracks, and in a way of making that self-healing, right? That the silica will migrate to those cracks, if the dynamics are right. So in addition to having dynamics that impact the properties, the dynamics of the polymer and the nanoparticles also impact processing. And perhaps the simplest example is if you add nanoparticles to the system, you go from a very simple viscoelastic liquid, that's the black data here. And as you increase the amount of nanoparticles, you go towards solid-like behavior. And that will impact the ability to injection mold intricate parts. So even if you have remarkable mechanical properties in the nanocomposite, you might still have trouble when you go to process it. And in a related topic, you know, during that injection molding process, when it's at that elevated temperature, the nanoparticles are likely to diffuse. And during that thermal injection molding at high temperature, you can also change the particle distribution. So the way the particles are distributed in the polymer matrix is critical for properties. And so this is just an example from Sanat Kumar's group where it's solvent cast, it's pretty well dispersed, and then they anneal it at a modest temperature for a long time, and now you actually start to build these aggregates, right? And so these are the sorts of things that motivate our study of focusing on the dynamics, the polymer dynamics and the particle dynamics in this, you know, wide variety of materials. Okay, so well, I'm just going to give you one more property example. We've started to think about polymer nanocomposites and how they might be useful in infrastructure applications. But for a lot of infrastructure applications, you need a composite that will have time-independent properties. Right? You don't want the composite to sag over a long time. So we've started to look at creep properties. So creep is you look you know, how much does the material deform under a constant load? And we can look at that by, in this example, we're doing elevated temperature dynamic mechanical tests, and we're pulling out the compliance. So this is the compliance as a function of time. And first you see that as we increase particle concentration, there's less and less compliance. So there's less and less flow as you put in more particles. But more importantly is how long does it take to get to this dashed line, right? And we can see that it goes out to longer times as we put in more particles. And then the other parameter we pull off of this is the ternary creep slope. So once it starts deforming at long times, how quickly does it deform, right? And so here, using, these are all silica particles with polystyrene, either in the bare silica particles or phenol capped. So this is really a weaker interaction in the green data. And then the red data is a strongly favorable interaction between P2VP and silica. And so you can see that this tertiary slope goes down as we put in more nanoparticles, and that's good because eventually we want this tertiary creep slope to be really flat, right? So we end up a very long time before failure. But in addition to the particle loading, we can start to see the importance of the particle distribution for these different examples. And then we need to worry about how the particle distribution evolves with time. So again, just all of this by way of motivation for what's going to be a fairly fundamental study of polymer dynamics and nanoparticle dynamics. Okay, so let's just start with what we know before we throw any nanoparticles in there. So polymer center of mass motion goes by a mechanism of reptation, which is based on a tube model. And I'll just remind you that, you know, a polymer is contained in a tube, and the lateral dimensions of the tube diameter is defined by entanglements. And so a highly entangled material, you know, with a small entanglement degree of polymerization will have a much denser array of entanglements, and that narrows the tube and makes diffusion more difficult. Okay. So, so this is a schematic trying to illustrate the entanglements, or you can just call them X's, and realize that the polymer here on the black line can't move through one of these X's because these are the entanglements. Okay, so we understand that the reptation goes as this prefactor to the molecular weight to the -2, and this prefactor has the friction coefficient, the temperature, and this molecular weight entanglement. Okay, so that's what we know. And this was well established theoretically and experimentally in the 80s. Okay. And so I also want to remind you that the length scale of this tube, particularly the tube diameter, is nanoscale, and that the dimensions of the polymer are nanoscale. And this is going to matter when we start putting in nanoparticles, because we're going to interfere with these different length scales. All right, so for polystyrene, the classic, the tube diameter is 7 nanometers. And for a modest molecular weight, the end-to-end distance is about 35 nanometers. So we're going to be looking at nanoparticles that are comparable in size. Okay. So if we want to think about how nanoparticles impact polymer diffusion, you know, there's the schematic, right? There will still be polymer entanglements. The local entanglement morphology or chain conformations might be distorted by the particles, but there will still be entanglements. And then the other thing that makes the nanocomposite situation a little extra complicated is that if you have randomly distributed nanoparticles, locally, they're not all the same distance apart, right? That's what random means. So sometimes particles are a little closer together, sometimes they're a little further apart. So there's inherently a diversity of local environments for the polymer chain to move through, right? And as I said, you know, we're going to be looking at particles that are on the same length scale as the polymer and the tube diameter. So I'm going to start the seminar by talking about a better defined system, and that is polymer dynamics inside rigid confinement. So thin films and cylindrical confinement. And again, the confinement length scales can be less than 100 nanometers. All right, so we'll call that nano confinement. All right, so we're going to start with rigid confinement and go to the nanocomposites. Okay, so thin films and cylinders, a lot of simulations and a little bit of experiments. And I'll just say particularly to the students in the audience, you'll notice that I'm not presenting our results in historical order. I just want to remind you, there's no reason to use historical order when you make a presentation. Just tell the story in the order that makes sense. So here we've done molecular dynamics simulations in collaboration with Rob Riegelman to look at polymers under confinement, both thin films and long cylindrical pores. And so the gray beads are the impermeable walls, and they have a amorphous packing, and they are immobile. And then the polymer chains are here. Each polymer has its own color. And we've defined a confinement parameter to look at the thickness of the thin film and the radius of the cylinder relative to the radius of gyration of the polymer. So we can look at that in comparison. And we're doing these simulations over a range of polymer lengths, number of beads, and also we're varying the extent of confinement. So a larger number here is larger confinement, and 0 is bulk. Okay, so that's the simulation, simple, traditional, coarse grains, Kramer-Gress sort of model. And the first thing we notice, and this is probably not surprising if you've thought about polymers up against rigid walls, is that there's a change in the polymer conformation. And so here we're comparing the confinement of the thin film and the cylinder, both as a function of this confinement parameter. And we've divided the change in the radius of gyration conformation into two parts, right? So you have this polymer and you have a radius of gyration. You can break that into a component that is perpendicular to the confinement direction and parallel to the confinement direction. So you have a confined parameter and an unconfined radius of gyration. So in the confined direction, hang on, I need to move the video window. There we go. In the confined direction, we were surprised to find that the extent of the collapse of the polymer chain was the same for cylinders and thin films. And as you go out to a confinement parameter of 10, you squeeze that radius of gyration in the confined direction by about a factor of 10. And then in the unconfined direction, so that would be in the plane of the thin film or along the cylindrical axis, we see that the confinement is more, the distortion of the chain conformation is more pronounced in the cylinder than it is in the thin film, which is the blue data. And that's pretty understandable from the geometry of the system. Now, the reason the chain conformations are important as we think about dynamics is that the chain conformations tell us how many entanglements there are. So here we're looking at the entanglements per chain as a function of the thickness of the thin film or the diameter of the cylinder. And when there is very little confinement, so we're way out here at the end, you can see it's very close to the bulk. The bulk are the dashed lines. And as we squeeze the thin film down, we can see that the number of entanglements decreases. And that's true if it's a thin film or a cylinder. And that's because that's because when there's a random walk for a polymer and it's up against a wall, the chain reflects back on itself. So I just took that segment and that segment of the polymer and flipped it back off the wall. So this chain segments are reflected off the wall. And if this polymer is occupying more volume near the wall, that means other polymers are displaced. So entanglements, you can only count an entanglement when it's two different polymers. So that's how we understand this drop off in the entanglements per chain as the system becomes more confined. Okay. Now, interestingly, those solid lines here are a very simple expression where we say that the center of the thin film or the center of the cylinders behaves like bulk, and then there's a region near the wall where there are no entanglements. And so that very simple expression gives us these curves that go through the simulation data very nicely, and we extract out this thickness, this depletion zone where there are no entanglements. And this increases with molecular weight, whether it's a thin film or a cylinder. Okay, so we can anticipate now that as we decrease the number of entanglements, we're actually going to increase the diffusion coefficient. And so that's what's shown here for the thin films. So as the film gets thinner and thinner, we can see the diffusion coefficient increases. And this increase in diffusion coefficient is more dramatic for the higher molecular weights because the drop off in entanglement density is larger at higher molecular weights, longer chains. Right? And so this is the schematic I showed you earlier, but now imagine that because it's confined, there are fewer entanglements. So I've kind of erased some of these entanglements, and that makes it easier for the polymer to diffuse. All right. Now I'm going to take a little break from the simulations, and I'm going to show you the experiments. And we actually did these experiments first. So we took an AAO, an anodized aluminum oxide template with these nanoscale pores. We filled it up with polystyrene. Then we put deuterated polystyrene on the top, and we let the deuterated polystyrene diffuse into the pores. And in doing that, we can get a concentration profile. So we measure the concentration profile using elastic recoil detection, which is an ion beam method that can tell you how deep inside your sample is the deuterium. And so this is a concentration profile of the deuterated polystyrene as a function of depth. The blue curve says there's a little bit of deuterated styrene that stays on the surface. And then the red curve is the concentration profile of the polystyrene that's able to diffuse into these pores. And again, without belaboring the point, I'll just show you one data set. And it clearly shows that the polymer diffusion is faster when the polymer is going into a cylindrical pore. Right? So it's 42% in this particular case. So it's an 18 nanometer pore. It's a pretty small pore. And it's going 42% faster than it would if it was going into a homogeneous bulk polystyrene. And so that's consistent with what we saw for the thin film. So let me show you now what we saw for the cylinders. And it's kind of the same. So as we go to a more confined system, we do see the diffusion coefficient increase, and then it decreases. So we have this non-monotonic dependence on confinement, whereas in the thin films, it just gets faster and faster and faster as the polymer disentangles. Here we know the disentanglement is happening. The disentanglement is actually even more sensitive to confinement than it is in the thin films. But so we see this upturn, it's more dramatic for higher molecular weights, and then it gets easier. First it gets faster to diffuse, and then it gets slower to diffuse. And this we understand because there's actually a phase separation or a segregation of the chains. So if you look at the lower right of the slide, when the cylinder is very small, the chains can no longer interpenetrate one another. They become these little plugs. And so this has also been seen, this is Lee's work from 2011, where this is a confinement parameter as a function of the radius of the pore. And I'll draw your attention to this, this curved line, which is separating the dispersed versus the segregated, right? And so the open pore, the open symbols here indicate the simulations that had this sort of segregated chain morphology. And so now we can understand why there's a turnover in the diffusion coefficient, because as long as the system is dispersed and you confine it more, you reduce the number of entanglements, and that should allow things to move faster until you get to a point where you've segregated the chains. And now it's and there's a huge entropic penalty for, let's say, the orange chain to move past the purple chain. They have to become very elongated to get past one another in this small diameter cylindrical pore. And that's what I've tried to represent here. So at high confinements, polymers and thin films have a much smaller entropic barrier than the cylinders. And so even when it's very highly confined, they can kind of do-si-do around one another in the thin film, right? Because they have two dimensions of motion. But in the cylinders, it's really one-dimensional, and it's a huge entropic penalty for the chains to pass one another and for center of mass diffusion to happen. Okay, so I think we have finished our first topic, polymer diffusion in confined geometries. So taking it one step more complex now, let's look at polymer conformations again, because conformations influence dynamics, polymer conformations and polymer diffusion in the presence of nanoparticles. And a few years ago, when I was thinking about this, I really wanted to know what was happening at the particles and far away from the particles. And so the scheme that I suggested to Rob was that we have a monolayer of particles. So now we can compare the diffusion really right between two particles, where things are going to be very distorted chain conformations and missing entanglements and stuff like that. But we can also see, as we go further and further away from these nanoparticles, how far that behavior persists away from the particles. And so I think of this as the princess and the pea experiment. Obviously, if you're right on top of the pea, you're going to feel it. But if you're further away, like 10 mattresses away, as the fairy tale goes, will you still know that there are particles there? And so again, we'll start with the simulations and then we'll go to the experiments. So this is the same sort of coarse grain molecular dynamics simulations. We're using nanoparticles that are composed of, glassy packing of immobile particles. It's athermal, so the interactions with the particles, the interactions with the polymers are the same as the interactions with the particles. We're mostly going to do this shorter chain because for the 200 bead chain just took a lot of computational time. So most of the results will be at 50. And we can vary independently and in a controlled way, right? We can independently control the particle size and how far apart they are. And so we can combine those together to look at, and then we can also define the confinement parameter, which is the interparticle distance now relative to the RG. All right, so relative to a real nanocomposite, when you have particles hither and yon, this is a much more defined system, and we can look at the impact of particle size and their separation on diffusion. Okay, so we're going to start with chain conformation. And so this is the top-down view, right? And so this is, surface of that particle, the surface of this particle, that's the interparticle distance. And then this is the side view, right? Okay, so the blue tells us that the chain is a little bit collapsed. And so this is the perpendicular component of the rate of gyration normalized by the bulk. And the only thing that we're changing here, it's all the same molecular weight, it's all the same particle size, we're just varying how far apart the particles are. And what you'll notice is that the extent of distortion, like the amount of squashing of the particle chain, is independent of how far apart these particles are, until the blue, this compression zone or this contraction zone, overlaps with the neighboring particle. And we can see that here. So this is all for the same system where we're just bringing the particles closer and closer together. The amount of distortion of the radius of gyration, it's relative to the bulk, it's down by 25%, and that's independent of how close the particles are. So the different colors here are different interparticle distances. It's the same RG for all of these data sets. And as we bring them closer together, you're getting contributions to that distortion of the chain conformations from both particles. And so if we look at the red data here, one of these curves, the dash curve, sorry, I guess it's the dotted curve that's a little higher than the simulation data, is if the amount of distortion of the chain only depends on the particle that you're closest to. And then the dashed curve, which is below the simulation result, says that you get equal contribution from both particles. And it actually turns out to be somewhere in the middle. So that's kind of interesting. The one thing I do want to highlight, and this is a little bit of a pet peeve I have with nanocomposite studies, is that I really think the important parameter when you talk about chain conformation is not the particle size. It's not really the interparticle distance, unless it gets very small. And it's not the polymer size. What's important is the nanoparticle to polymer ratio. Right? The extent to which a polymer is distorted by the particle depends on both the particle size and the polymer size. And that's clearly represented here, where the red data is the smaller chain, the green data is the bigger chain, but the symbols tell you what the ratio is. And so both triangle sets sit here, both circles sit here, right? So we need to think about that ratio when we think about the chain, the distortion of the chain conformation. Okay, so let's get to the dynamics. So like I said, this is the princess and the pea sort of experiment. And we wanted to know what the center of mass polymer we wanted to know what the center of mass polymer diffusion coefficient was as a function of distance away from the particles. And so we looked at each bead and followed its trajectory, and then calculated its average distance from the particle monolayer. And that's how we binned the data. So we'll have diffusion coefficients where the beads primarily were far away from the particle, or not so far, closer and closer, or even inside the particle monolayer. All right. So that result looks like this. So, inside the monolayer, the diffusion coefficient in the z-axis is a little bit higher than it is in the bulk. That's where there's a lot of chain distortion, there's a lot of disentanglement, so things should be faster. But the diffusion coefficient away here is actually much smaller. And it's more distorted, like the diffusion coefficient relative to the bulk, it's further away from the bulk for a tighter packing of the particles, a smaller ID over 2RG. And so that's interesting, that we can slow down the diffusion coefficient relative to the bulk. And the other thing that's interesting is this persists for quite a long distance away from the particles. So this is RG. This is, so like out here it's you're 6 RGs away, and you're still 5 or 10% slower in center of mass diffusion than you are on the bulk. Well, one more piece of analysis on this is we can look at each of these particles and do this Van Hoeve distribution analysis. So the Van Hoeve distribution, as a reminder, is at time 0, you think of the bead as being at the center. And then at some later time, you see how far it is moved, right? And you can calculate, and you basically do the analysis and you get a distribution function of the probability of it being delta Z away, right? So we're only looking at the Z direction. So the most probable is that it hasn't moved off of Z equals 0 at all, and it'll be symmetric in both directions because this is the bulk, right? And at longer and longer times, so from the dark to the light blue, the distribution just spreads out with time, right? So that makes sense for diffusion in an isotropic polymer melt. And then the width of this distribution function goes as delta T to the half, and we can extract a diffusion coefficient. All right, so that's your reminder of the Van Hoeve distribution for dynamics. And we can do this for the monolayer. So we can look at different Z0 positions, right up against the particles, a little further away from the particle, a little further away from the particles. And we can look at the distribution function, keeping track of whether you're moving towards the particles or away from the particles. And the raw data is the dashed curve. And well, you know, it's got this weird dip, but that's because, you know, we're really close to the nanoparticle monolayer, and diffusing into the particles will be depressed because the particles are taking up a lot of space. But we can correct for that inaccessible volume by using, we can just calculate that. And then we have the corrected data, which is the solid curve. And what might be hard to see from this is actually there is anisotropy to that solid curve. It is no longer Gaussian. And so here I've reproduced the data that was on the previous slide. So the bulk is in the open circles, and that you fit with a nice symmetric Gaussian. And then for the monolayer, where we're right outside the particles, those are the filled circles. And you know, you're fitting it with 2 different Gaussians, or 2 different half Gaussians, to fit diffusing away from the particles as opposed to diffusing towards the particles. And now we have the interesting result, which is the diffusion in the Z direction is nearly the same as the bulk when you're diffusing away from the particle, but diffusing towards the particles is slower. And that's interesting because when we were in confinement, you know, we know that there's a change in the chain conformation. So there'll be less entanglements in where the particles are. It's less entangled there. And that you would suspect would have a faster diffusion coefficient. But because of additional factors, so, you know, the distortions to the chain conformation more wholly, not just the loss of the entanglements, we can see that the diffusion coefficient going into the monolayer is actually depressed. It's moving slower. So we can just put those 2 ideas on the same slide here. So in the rigid confinement, you know, we're losing entanglements because of the distortion of the chain conformation. So things get faster until this funny thing happens in the cylinders where things have segregated. But the increase in confinement here, when we're going to a smaller and smaller interparticle distance, we're going more and more confined, we're actually getting a decrease in the diffusion coefficient, right? And this is because there are entropic penalties to squeeze into those little tight spaces, right? So in that way, the monolayer is behaving a little bit like the segregated cylindrical system. And the other thing that's important to note here is that this is a very critical parameter, this interparticle distance relative to the RG. You know, that's how much the polymer chain has to distort to get in there. Okay, so this is to remind me to take a sip of water. So now I'm going to show you the experiments. The experiments came first. So the way we measure polymer diffusion is like I explained earlier with the anodized aluminum oxide templates. We have a helium ion beam that knocks out the deuterated material, and we can use the detector to give us the energy of the deuterium. And so if we have a deuterated tracer, red, and it is, we put a little bit of deuterated material on top of a bulk composite, we can look at the concentration of the deuterated material as it goes into the composite and as a function of time and temperature as it's annealed. And so this concentration profile can be fit with Fick's second law, and the only unknown in this equation is the diffusion coefficient. We know the initial thickness, we know how long we annealed it, we've measured the concentration profile as a function of X, and now we just have the diffusion coefficient. Okay. So the very first diffusion experiments we did were with carbon nanotubes, and thinking about how the carbon nanotubes would disrupt or not the entanglements and how that might impact the diffusion coefficient. And we had this very unusual result. So as we added more nanotubes, we first saw a dramatic drop in the diffusion coefficient. You know, so with half a volume percent of nanotube, the diffusion coefficient is dropping by, you know, 80%. For the smallest molecular weight, and it's not as dramatic for the highest molecular weight. So we have this dramatic drop in the diffusion coefficient, then afterward it recovers. And this was really puzzling because this minimum corresponded to the critical concentration where we got electrical percolation. So that means we had a percolated network. And so time went by, and then Russ Composite had a fabulous postdoc, Ji-Hoon Choi, who made nanorods with different lengths. I mean, the nanotube experiments are inherently complex because you don't have good control over the length or the diameter. So Ji-Hoon synthesized these nanorods, and we found that there was a particular condition that had to be met for the diffusion to go through this minimum. And so the diffusion minimum was only observed in this red quadrant. And in this red quadrant, for nanowires, for nanorods, or for carbon nanotubes, the polymer, the size of the polymer was large relative to one dimension and small relative to the other dimension. And so that minimum really has to do with whether the polymer that is moving sees that object as anisotropic. And then if it didn't, like if the rod was kind of chunky or small in these two extremes, then the polymer did not identify that nanorod as being anisotropic, and it just the diffusion coefficient just decreased with increasing loading. All right, so we think this has to do with how the polymer chain drains over highly anisotropic particles. Yeah, the theory in this area is very limited, so there's still a little bit of hand waving on the interpretation, but I think this is a really good clue that the particles have to be anisotropic relative to the size of the polymer. Okay, but let's go back to spheres because, you know, that's much simpler. So it's the same sort of experiment, deuterated polymer on top of the nanocomposite. We measure the concentration profile and extract a diffusion coefficient. So from the TEM, you can see that we have nice, well-dispersed nanoparticles even to high concentrations. And as we add nanoparticles, the diffusion coefficient decreases. So again, not like the confinement, the diffusion coefficient decreases quite substantially and for a range of molecular weights. So to put this all together, like we have a particle size, we have a concentration of particles, and we have a polymer molecular weight. We developed this idea of a confinement parameter back in 2011 with this first set of data. And so again, the interparticle distance is the surface to surface particle separation. And you can calculate that using this expression, which is the diameter of the particle and the concentration of the particles, assuming you have them well dispersed. And now we can see that this is the normalized diffusion coefficient relative to the bulk as a function of this confinement parameter. And we can see that independent of the molecular weight of the particle, of the molecular weight of the polymer, we get really nice collapse for these three sets of materials, these three sets of polymers. And interestingly, at an interparticle distance that's quite a bit larger, ID over 2RG is 3, we're still 20 or 30% below the bulk diffusion coefficient. So even very far separation of particles still has a significant impact on the polymer diffusion coefficient. And so this was the first time that Russ and I used the ID over 2RG parameter. And then there were many more papers, and I'm just going to skip to the end, where this is a compilation of years of work, where this is the bare particle, the gray data points. You can just see how lovely this collapses for polystyrene on silica, phenylcap silica. So again, a very athermal surface. If you have bare particles, if you have particles with a low grafting density or a high grafting density. The only tweak that we had to make to get this normalized diffusion coefficient to go as the ID over 2RG is to use the effective interparticle distance. And so that just means if you have a grafted polymer brush, right? So if you have this black grafted polymer chains on the particle, the diffusing species doesn't get all the way into the surface, right? Particularly when it's high grafting density, it can only get part way in. And so we used mean field calculations to give us this effective diameter. And once we use the effective diameter, which is bigger than the nanoparticle, once we use that effective diameter, calculate the interparticle distance, everything collapsed beautifully. So now let's just look at those results. So when the interparticle distance is very small relative to RG, the diffusion coefficient is going to drop by a lot, maybe even close to an order of magnitude when the particles are really tight, right? And that's going to impact how they respond in flow and how they respond to mechanical properties. But what's always interested me more, or maybe just as much, is that this is a very long range effect. So, we had to work really hard to make these very dilute nanocomposites systems, right? But now we're out at an ID over 2RG of more than 10, and we're still seeing a decrease in the diffusion coefficient. And this is one of the reasons why we did those monolayer molecular dynamics simulations, to really convince ourselves that it's a princess and the pea, like the center of mass polymer diffusion, even if it's very far away from those nanoparticles, is impacted. And that is hard to understand why. It's hard to imagine that there's that chain that's so far away, that the entropic, the entropy of that chain and its chain conformation could be so distorted that it would still change the diffusion coefficient. So there you have that. Okay, in the last few minutes, I just want to share what we've done with particle diffusion. And so the first set of experiments are going to be about an ensemble where we look at a whole bunch of nanoparticles moving. And then like it's shown here, the single particle tracking where we're looking at one particle moving at a time. Okay, so first with the ensemble, this is another ion beam method. It's a little different in the sense that we now have a composite and it's on top of a homopolymer. And we look for the particles to diffuse in, right? So as a function of temperature and time. So this experimental method is called Rutherford backscattering. It's helium in, helium out. And the energy of that outgoing helium tells you how deep inside the sample is the silicon. And so this is the silicon concentration profile. And just like we did before, we can get a diffusion coefficient from that concentration profile. The chemistry that we used in this set of experiments is P2VP, which has a very favorable interaction with bare silica. So that nitrogen likes to nestle in with that OH group, and we have an attractive interaction between the polymer and the particle, and we're going to watch how that particle moves. So here's the data. This is the diffusion coefficient now as a function of molecular weight. And as you suspect, as the molecular weight of the matrix increases, the diffusion coefficient decreases because you're increasing the viscosity at a fixed temperature. And then for comparison here, I put the blue data, which is calculated from the Stokes-Einstein equation. So the Stokes-Einstein equation assumes that the particle is diffusing just based on random Brownian motion. So just, you know, the monomers are just acting independently and hitting the particle and making the particle move. And so it's the diffusion coefficient based on Stokes-Einstein has a temperature and viscosity piece, and it depends on the radius of the nanoparticle, right? So, so it looks like things are moving slower. Well, partly it is moving slower than the Stokes-Einstein approximation. So we can understand that by understanding that the polymer that is absorbed to that particle is absorbed for a long time. And so it is absorbed and it's moving in with the particle, right? So the strong interactions with the polymer and the particle create this bound layer, and that whole entity moves. So if we can extract, if we can use the Stokes-Einstein equation to extract an effective radius. So this is the bound layer and the bare particle. So the bare particle, of course, is molecular weight independent, but the bound layer, this effective diameter of the particle increases with molecular weight. And if we just look at H, which is that difference between the particle size and the particle and bound layer, so it's just the bound layer thickness, it increases as the molecular weight to the 1/2. So we can put that back into the, oops, sorry, I didn't show you that slide. Anyway, so if we put this dependence into the, back into the expression, it fits lovely. So Stokes-Einstein works even for nanoparticles as long as you know the size of the entity that is moving. And so maybe it's the bare particle, but maybe it's a bare particle that is that has an attached polymer chains around it. Okay, last thing is, I'll just go ahead and start the video so you can watch the little dots move. So single particle tracking is widely used in liquid systems to watch particles move, but we used it to look at a polymer melt. So we went to a new polymer, which was much lower in TG, because we wanted to look at the effect of this bound layer as a function of particle-polymer interaction. Now, if you have a good, strong interaction, you're going to have a bound layer, and that bound layer is going to prevent polymer agglomeration. But if you have a neutral surface, the particles are going to find each other and get stuck. And these diffusion experiments are long, so we really need to find a way to circumvent particle agglomeration, because we don't want to measure, you know, groups of particles moving. That would be even slower. So we went to single particle tracking so that we could look at the effect of the particle polymer interaction. And so here's our polymer. It's polypropylene glycol, nice low TG material. And we looked at two particles, non-sticky, just with the methyl functionalization, and then sticky with the carboxylic acid groups. And this is just, you know, nearly 2,000 traces where we've started them all at 0, 0, and you can just see that it's nice and isotropic. So, and then you do a lot of analysis of those individual traces to back out the diffusion coefficients, right? So there's the mean squared displacement as a function of time interval. And this is for different molecular weight polymers. And you can see out at these long times, we have nice diffusive behavior. And as we were hoping, we saw two different diffusion coefficients. We saw a measurable difference in the diffusion coefficient for the sticky and the non-sticky particles. And so the sticky particles, you know, have this adsorbed polymer chain on it. So this dashed line now is the Stokes-Einstein approximation where we're using R effective. And R effective is the core nanoparticle size plus Rg. And so Rg increases with molecular weight, of course. And it goes, and actually it goes as molecular weight to the half because we're in a polymer melt. And so that's how we capture, that's how this the modified Stokes-Einstein fits with this dashed line. And in the case where it's a non-sticky particle, then we just use the core particle because there's no polymer sticking to it, and that captures the data, right? This is just the diffusion coefficient relative to the Stokes-Einstein with the bare particle. All right, so the single particle tracking was very important to make clear that this adsorbed polymer chain is because of the specific strong interaction and is absent, and that Stokes-Einstein works when you have a bare particle. And now what we're going to work on is, you know, this is like black and white with regard to strength of interaction. And now we're just going to work a little bit in between those two with kind of two questions in mind. One is, how does it impact the diffusion coefficient? But how long lived is that adsorbed polymer chain? Because that'll give us some insight about if the polymer chain is absorbed for a very long time, it's unlikely the particles will agglomerate. But if the polymer is coming on and off that surface, that opens up a window for the particles to agglomerate and aggregate. So that's where we're headed next with polymer dynamics and nanoparticle dynamics. So with that, I want to thank you again for your attention, for having yet another Zoom hour in your day. And like I said, what I was able to share with you today is polymer dynamics, nanoparticle dynamics in confined systems and in polymer nanocomposites. I think understanding the dynamics of these systems is very important, both with how they perform, their properties, and how we can process them. And if you want to know more, my website's there at the bottom if you want to check out the papers. Thank you.
All right, thank you, Karen. Let's all thank Karen with maybe a virtual clap here. Very good. And we'll transition here to Q&A, and I'll open it up here to the audience first. If there are any questions, you can raise your hand. You can type it in the chat box. Or if you're bold enough, oh, I see a raised hand already. And it looks like Michael has raised his hand first. So Michael, please.
Hi, Karen. Really nice talk. Thank you very much. I'm curious, in kind of the second story you talked about the nanoparticles. So you're measuring diffusion coefficients, which look at like the reptation and kind of the larger scale dynamics of the polymers. I'm curious, does the data you have any implications on like the segmental dynamics of the polymer, like individual polymer segments, especially in the vicinity of the nanoparticles?
Right. So we've done some segmental dynamics as well, but you know, that was long enough. P2VP and silica has also been studied a lot by Alexei Sokolov's group. Right at the nanoparticle, that strong interaction does slow down segmental dynamics. And so you can see that in an electrical impedance spectroscopy. You can also see it in a different TG, in a higher TG. Once you have enough particles there, you've distorted the segmental dynamics, or you slowed the segmental dynamics of enough segments that you can pick it up in DSC, even modulated DSC. And we just published a paper in, using quasi-elastic neutron scattering, where we had two different P2VPs, where one, the whole chain was deuterated, and the other, only the ring was deuterated. And the slowing down happens in both the ring and the backbone. So it turned out not to be that interesting.
Great, thanks.
Sure.
Okay, thank you. There's another question from Niels.
Yes, hi Karen, this is Neil speaking. Thank you very much for a super fascinating talk. Can you go back one slide to slide 56, please?
I believe so. Oops, wrong way. There?
Thank you. So in this slide, this is also, yeah, I'll try to limit it to one question, but this slide is super fascinating. So if there was a third axis of temperature on this plot, right, would you expect those two curves to sort of collapse at some point? So basically, this is obviously these time scales of interactions obviously dependent on temperature, right? And this is sort of a plot at one temperature where one is stickier than the other. So if you had a third axis of temperature, would the red data eventually just become the black data?
That's a good point. So would temperature eliminate that favorable interaction?
Yeah.
Yeah.
Speed it up so much that you wouldn't expect to see this deviation anymore.
Right. It's a hydrogen bond. So yeah, temperature should be able to knock that out.
Okay.
The downside is our single particle tracking system only works at room temperature.
Okay, got it.
Because
Yeah,
it's
so
designed,
that's
designed for water.
that makes it difficult. Yeah, okay.
That's a great point, and I think the next round of experiments we're thinking about for particle diffusion is probably not going to use single particle tracking. We have another set of experiments that we're trying to learn that I think will be more versatile because temperature is important.
Yeah, yeah. Thank you.
Sure.
Great, thank you, Niels. Another question from Kyle.
Yes, thanks so much for the really nice talk. I really enjoyed that. I wanted to ask you about polymer dispersity. I know that's kind of a tough question usually, but in particular, you were talking about how the importance of this ratio of the interparticle distance and also the polymer radius of gyration. And then I think, if I understood correctly, at one point there was a difference in the diffusion away from particles and towards particles. And I was curious if that would actually cause like a segregation of smaller chains and larger chains near particle surfaces.
Thank you for asking that question. It is so that we did in molecular dynamics simulations. The polymer density, the bead density, is the same everywhere. If I go back to that slide, well, I won't go back, but the diffusion coefficient tells us about the width of the Gaussian, but you also notice that there was a displacement in the maximum intensity. And so there is no buildup because the ones that are moving faster, there are fewer of them, I think, than the ones that are moving slow, there's more of them. So the fast and slow motion is compensated by the number of polymers that are diffusing. So the density, the polymer density is uniform throughout this entire simulation. I forgot to say that, sorry.
I guess can I extend that for a second? So like if it's uniform everywhere, does that still mean that like if you had a mix of shorter chains and longer chains?
Okay, if we had a mixture of no, that's a great thought experiment. That would be complicated to think about. Okay, now I really do need to go look at that result. So this is what we want. Oh, so while we're here, oops, so Kyle, you can see the red curve on the left and the green curve on the right have different heights. All right.
Mm-hmm.
All right. But your question was, I want to look at, okay, we can look at this. Yeah, we'll look at this. So this is all for the same molecular weight. But if we had a higher molecular weight, so if we look at this, if we had this set of data, and then we mixed it with a larger polymer, we would have this set of data. I don't know what would happen. I mean, I don't know whether that local environment would cause a partitioning of the different polymer molecular weights, because squeezing between the particles is easier if you're short chain. You know, it's less of an entropic penalty. And I don't know if the polymers would stay mixed. Yeah, no, I don't have a.
That's quite all right. I'm glad that's a hard question.
I have to think about it in multiple dimensions at the same time, and I've been on Zoom all day, so not my best thinking. Great question though, thanks.
Thank you.
Great, thank you. I think we're actually coming up on 4:45. So David, I think you can have the last question here for today when you're ready.
Okay, great. Thanks, Zach. Hi, Karen. I thought your presentation was really, really cool. I'm glad you were able to give a talk here today. I have a couple of questions about your simulations of the polymers in confinement. I guess the first one, I remember you presented some data about the number of entanglements per chain in your simulations. I'm just curious, how do you like count entanglements in simulations? Like, how do you figure out what like intermolecular interaction is an entanglement and quantify that?
Right. There's some really, so there are, I'm not going to remember whose program we used, but there are, you know, for sharing programs that do this calculation for regular MD. And the visual you can have is, okay, you have a whole bunch of high molecular weight polymers and they're entangled. Pin their chain ends. All right, pin all of the polymer chain ends and then shorten the polymer. So you basically, I think it was like each chain end has like little rollers and you're just rolling up the squiggly string to a tight string. And then what happens, you go from these random walks to like zigzags. And then every place where the chain, ultimately when you get them to their very shortest length, and you're doing this on all the chains simultaneously. So then once you have all the chains to their shortest length, you look at each chain, and wherever there's a change in direction, like a line segment, that's how you count the entanglements.
Cool.
It's much better if you can see the movie, you know.
I bet it would be a cool movie. Can I sneak another quick question in? So the polymers in the really confined cylinder were like plugs, you said? Mm-hmm. Between the two sheets, do they form like tiles but can still diffuse relatively quickly?
So to the extent of, we actually looked for that very carefully. And we looked for the propensity that you would find a bead from your same chain as opposed to a bead from another chain. So kind of like your self environment. And as we get more and more confined, there is a slight tendency towards that segregation, but it's slight. And so we might have to go, we might have to go very, very thin to drive that segregation, but we didn't see segregation. We saw a weak trending towards segregation.
Okay, cool. A couple more minutes, sneak another question in, unless someone else has their hand raised.
Well, Zach, if you want to let the audience go, I can.
Yeah, I think what we'll do, similar to an actual seminar presentation, I'm sure there are more follow-up questions, and if it's okay with you, Karen, to stay on the line for a little bit, I may ask a few as well, but I think we can end the seminar for the entire group. But those who want to stay around and ask a few more questions, please do. But before we end the presentation today, let's give another round of applause, a virtual round of applause for Karen and the really nice presentation. Karen, thank you again for joining us here virtually at MIT. We really appreciate the talk, and it was really good seeing you. take care. I'll stay on the line again, but others are free to leave if they need you now.
Thank you.
All right, David, you can keep going.
Great. I think it was around slide 42 where you had this really nice plot of like nanorod aspect ratio dimensions versus like polymer diffusion.
Yeah. Yeah.
Can you pull that up really quick?
Sure. I'm just going to zip through these. Yep, there it is.
Okay, so I think maybe I missed this point. Can you give like a one sentence summary of like the conclusion from this?
Sure. So what we were tracking was whether or not there's a minimum in the diffusion coefficient as you put more nanoparticles in, right? So when do you see this minimum? Because we were able to make it go away even in nanotubes if we had certain sizes. Anyway, so when do you have this minimum and when does it just monotonically decrease with the addition of particles? And so this red zone is where you see this minimum. And you see that minimum in the diffusion coefficient because the polymer detects an anisotropic particle. And the best, it's very hand waving. And if you think about it too deeply, it's flawed. But somehow the diffusion coefficient, this, perpendicular to the nanorod and along the nanorod are different.
Yeah.
And that's where we started thinking about it. It's draining over the nanoparticle and, it doesn't know if it's going to go to the left or to the right of the nanoparticle and, until it's pretty far gone, as opposed to moving along the nanoparticle. I don't think we have a really foundational understanding of that anisotropy of the diffusion coefficient. I don't think we really have a good mechanism.
Okay, can I so I guess, my intuitive picture is sort of like, you have this really skinny needle and it can sort of like, I guess I'll take one step back. On like the next slide, you're measuring like polymer diffusion coefficient, but like, what about the nanorod diffusion coefficient, right? Like your polymers are moving, but if you have like a particle that can potentially move faster than another particle, is that going to have like some?
Right, that's a great point. I forgot to mention that too. So when we're looking at polymer diffusion, we are doing it at temperatures and with large enough particles that the polymer is diffusing about 100 times faster than the particle.
Okay.
Okay, so when we're talking about polymer diffusion, the particles are effectively immobile.
Okay.
Now, Jihoon and Russ also have a paper about particle diffusion, nanoparticle diffusion, rod diffusion, and there is a difference. They move along their axis faster than they do laterally because it's kind of like reptation, right? You're running into entanglements if the rod moves left or right, but if the rod goes straight ahead, it's faster.
Okay, cool. That's interesting. I guess another quick question. Do when you have these really high aspect ratio nanorods, even if like the center of mass has a relatively low diffusion, are the tips like moving relatively, much more quickly than the center of mass?
You mean like wobbling?
Yeah.
No.
Okay.
But actually you bring up a point. Like, so if they're, they're really stiff, right? Particularly the squares and circles, these are oxides. They're not bending, but they can move, they can jiggle. And the jiggle might allow for faster diffusion perpendicular to the rod than along the rod. Yeah, no, that goes the wrong direction. But yeah, we don't have a great mechanistic insight here.
Cool. Thanks for answering my extra questions.
you.